All right, Physics 2, welcome back to part 2 of Wednesday's lecture. Continuing on with chapter 21 and developing a deeper understanding of Gauss's law. So last time we had just used Gauss's law to get Coulomb's law. So that would be E is equal to Q over 4 pi epsilon naught 1 over r squared for a point charge. Now we're going to go ahead and just take a quick look at the reverse. So let's consider a point Q surrounded by an imaginary sphere. So we know that the electric field would be equal to 1 over 4 pi epsilon naught Q over r squared, Coulomb's law. Okay, so using Gauss's law, looking at the surface integral of E dot dA is equal to surface integral of 1 over 4 pi epsilon naught Q over r squared dA is equal to Q over 4 pi epsilon naught r squared times, if we integrate dA, once again, we're going to get the surface area of a sphere for, that's a pi r squared. We see, and we're left with Q over epsilon naught being equal to E dot dA. There you go. So we can see that one can be used to show the other. Pretty cool. All right, so works for a sphere. Spheres are easy. So spheres are pretty easy. You know, they're symmetric. So let's look at some more general situations. All right, so if we look at the formula again, now we're going to think back to our 2-point charges. So this would be the situation where we have the positive charge and the negative charge, and okay, so we can see that there's the distortion of the lines. Let's put some Gaussian surfaces around them. Okay. All right, for both of these, we have the same number of lines. Makes sense, as the magnitude of plus Q is equal to the magnitude of minus Q. So for both these charges. All right, for the same distance, of course. All right, so therefore, the flux is proportional to the number of lines. So the electric flux is going to be proportional to the number of field lines. Therefore, the flux for both charges is the same. So remember, so this one's area 1, that one's area 2. So we have the surface integral E dot dA for A1 is equal to the surface integral for E dot dA for A2 is going to be equal to Q over epsilon naught. And this holds true for any surface. This is always true. Now, that being said, some surfaces are easy to calculate than others. So, you want to think about, what do you feel like integrating? All right, so let's keep building on this particular concept. How would we do Gauss's law in the case that there are lots of charges? So lots of Q's in a surface area. And in which case, no problem. So let's say we're going to call these QI's enclosed. In that case, EI dA would be equal to QI epsilon naught. So Q is the sum total of all the charge. So EI is the electric field of each charge produced by QI. And using the superposition principle, you could just sum these together. So we can see this from superposition principle. We can sum the fields. And you get that the electric field is going to be the result of all of the electric fields in, or all of the electric fields of all of the charges inside summed together. Therefore, the surface integral E dot dA is equal to the surface integral of the sum of all of the field contributions times dA is equal to the sum of QI over epsilon naught, which is Q enclosed over epsilon naught. So for this case, the sum of QI is equal to Q enclosed. And this was even true in the first iteration that we saw. So all this will tell you is the net charge. So one important note about the differences between Gauss's law and Coulomb's law. So there are limitations on Coulomb's law, which we kind of hinted at earlier. It's still a very powerful law, and sometimes it's the easiest way to solve something. But Gauss's law holds true always. You can use it in any situation. It's just that some situations are harder to calculate than others, but you can always use it. So, and just to reiterate, just the power of Gauss's law tells us that input and output flux of the electric field over a surface is due to the charge within the surface. All right, so now that we understand what Gauss's law's formula is and generally what you can use it for, let's do some examples to really flesh out just how we can use this tool. So let's say we had a charge plus Q, and we've got two Gaussian surfaces. So the surface that you're enclosing space in to look at the field lines is called a Gaussian surface. So Gaussian surfaces. All right, so we have the field lines coming from this charge, puncturing this surface, radiating outwards. These keep going. And so we see, this is surface area 1, surface area 2. So we can see that both of these Gaussian surfaces have field lines going through them. But plus Q is only enclosed in A1. It's the only charge. So, what is the net flux through each surface? So A1, this contains Q. Therefore, flux is equal to Q over epsilon naught. Easy peasy. And A2 contains 0 net charge. So therefore, the flux is equal to 0. If there's no charge inside, then the flux is 0. Flux is about the charge inside, not field lines going through an area from an external charge. So in the dipole that we looked at before, it is true that you would see some field lines from the other particle. They are not contributing to the flux. They are not inside that surface. So, and one thing to note that would be an indicator that this has no charge inside is all field lines that enter also exit. Unlike this charge here where we have field lines, so this field line is exiting. If this was a negative charge and they were coming in, they would be entering but not exiting because it is the source of the field lines is inside. All right, so moving on. To applications of Gauss's law. So Gauss's law, as I'm sure you can see, is used in a wide number of physics situations. It is particularly useful when you're dealing with symmetrical situations. So typically when you're setting up your Gaussian surface, you're going to look for a symmetrical surface. So typically used, but you don't have to. It does not have to be symmetrical. It's just easier if it's symmetrical. Situations, but not required. All right, so typically, I think I'm going to change that to useful. It's very useful if it's symmetric, very easy to set up. All right, so let's walk through some examples. So in these examples, we're going to be choosing a surface. So, and this is going to be relevant for this class as you progress. If you do more electromagnetism, you're going to see this be less and less the case. But we're going to be choosing surfaces with a constant E on all parts, or segments where it's constant that you can then sub together. So this is just an easier thing to do. So for example, let's do a negative charge this time. So we've got the field lines. This is going to be the same at every location on the surface. So constant E at every point. However, if we were to take the same negative charge and enclose it now in a box, we'd see this is not the case. So here you have the same radius all the way around. Here you've got the diagonal, you've got the horizontal, you've got the vertical. So we have not a constant E. And so if you're allowed to choose your surface area for the problem setup, this is the easy one. This is easy. This is hard. It's true you could get the right solution either way. Go with easy. There are no cookies for doing things the hard way unreasonably. All right, so let's use Gauss's law to look at a spherical conductor. So we have a thin spherical shell of radius R0 that possesses a total net charge of Q that is uniformly distributed. Okay, so we want to ask the following three questions. What is the electric field outside the shell? What is the electric field inside the shell? And what if the sphere was solid? All right, so let's look at part A. So we've got our sphere, and we've got our radius, R0. And we wanted to look at a spot inside the shell. So let's call that R2. We wanted to look outside the shell. Let's call that R1. So then let's draw some Gaussian surfaces. So here's a Gaussian surface for R2. Here's a Gaussian surface for R1, so we'll call that A1, call this A2, and let's give it some field lines. All right, so we're dealing with a shell, so the field lines are all going to be on the outside of the surface. And then we have previously proven that everything inside cancels each other out. So this is 0 inside. Okay, so we can see that if we look at the surface, that the electric fields, if properly drawn, are perpendicular to the surface. Therefore, cosine of theta between the electric field and the surface area point is always 1. Beauty of our setups. Okay, so let's go ahead and use Gauss's law. So the surface integral E dot dA is equal to E times, so remember, this is just looking at summing over that surface area. So make sure you know surface areas, 4 pi R1 squared. So this is just going back to our drawing here. This is R1 is equal to Q over epsilon naught. E is equal to 1 over 4 pi epsilon naught Q over R1 squared for R greater than R naught. Okay, we've seen this before. We've just, in my opinion, Gauss's law is really just a more beautiful way of doing it, but we're not surprised by this. Actually, we're not going to be surprised by anything. We're just going to see a new way of thinking. All right, so next up, we have inside the field must also be symmetric. But Q enclosed is 0. So going back to our picture, remember Q on a shell is on the surface. So there's nothing in here. So there's nothing to give it any field whatsoever on the inside. So if you look here, there's nothing that is producing a charge that is enclosed. So we can see, therefore, the surface integral E dot dA is equal to E times 4 pi R2 squared is equal to 0. Thus, E is equal to 0. Because this is non-zero, therefore it must follow that E is 0. And that is because there is no charge enclosed within this surface. All right, so let's look at solid spheres. And we'll look at a conducting solid sphere. All right, so this changes nothing. So we have previously shown that with a solid sphere, all of the charge is still going to go to the surface when you're dealing with a conductor. Those electrons are free to move and they're going to go to the surface. So it is still going to be true that it's going to be 0 on the inside, and it's going to look like a point particle on the outside. All right, so next time we're going to look at a solid sphere of charge, which is more steps than I have time yet to do in this particular lecture, and we'll step through how to approach that using Gauss's law. So I will see you next time for part 1 of Thursday's lecture.